All right, so last time we explored one-dimensional Lagrangians, where you had a configuration space that was only a single dimension, and again, the goal of, or the basis behind the idea of Hamilton's principle is that nature takes the path that optimizes the integral of the Lagrangian over time. And we can find what that path is for our given generalized coordinate by evaluating Lagrange's equation, which is given, of course, right here. For whatever our coordinate is, if we can first write the Lagrangian in terms of that coordinate and its derivative, and maybe also time, evaluating this Lagrangian then gives us a differential equation that, when solved, gives us the trajectory, which is the optimal path of the action integral. But let's extend that. What if I have a configuration space that is multiple dimensions? And let's just take the simple case of a ball thrown not vertically upward, but it has some horizontal motion. In this case, the number of objects is 1. The number of dimensions it's moving is 2. And there's no constraints. So the dimensionality in this case is 2 times 1 minus 0, or just 2. I should expect to be able to write the entire configuration of the system, in this case a ball being thrown into the air, but it requires 2 coordinates. So I can't just have a q, but I expect to have a q1 and a q2 that can label my system. And the natural choices in this case might be x and y. Give me x and y and its derivatives, and I can write down the entire Lagrangian for this system. In this case, L, which is going to be t minus u. It's going to be 1/2 m v squared minus mgy. And then the v in this case is just going to be x dot squared plus y dot squared minus mgy. So this Lagrangian now has both, it can be written in terms of x. So this Lagrangian is a function of x and x dot, y and y dot, and then maybe t. Some of these don't appear. Like there's no x, for example, but there is an x dot. And both y and y dot appear, and there's no explicit time dependence. But in this case, how do I find the optimal path in this case? Because I can't just, do I evaluate just one Lagrangian, pick x or pick y? Because I can't write them in terms of each other again, because there's no constraint between the two. They can be completely independent of one another. What's going on, and how do we solve this? Well, if you consider back the original proof, if you go back to the proof of how we derived the Lagrangian in the first place, right, before we said what? We said that we took some path y that was y naught plus some alpha times eta. Remember, y naught was the actual path we were trying to figure out, and then alpha was an arbitrary constant, and then eta was a function that allowed us to encapsulate any deviation that you had from the true path. And we did an optimization integral. This then, remember, became the action in this case, which was originally just a function, an integral over f. S in that case then became a function of alpha. And then we found where ds d alpha equaled 0 and used that to figure out the optimal path in this case. And that is what we did for one dimension. We can apply the same argument when there are multiple dimensions. So for multi-d, and I'll do it for the problem above, and you'll see how it generalizes. Assume that x can be written as some true path that it takes in the x direction, plus alpha times, and I'll do epsilon. And then y is similarly its true path plus alpha times eta, where eta and epsilon are functions of t, as are x naught and y naught. Those are the actual paths. And then we're again allowing for the true path plus some deviation that is a function of alpha. This then turns the integral of s, and I'll just write as the Lagrangian, x dot, y dot, t. This makes s, again, a function of alpha, and we can find where ds d alpha at alpha equals 0, just like we did before. And before we had lots of messy partial derivatives, and you can go back to the module and see how that proof kind of laid itself out. We essentially do exactly the same thing here, but just now we have to take into account that there are just more variables. There's not just y and y dot, but we also have to consider partials of x and x dot as well as we take time derivatives or alpha derivatives or all that such. And so I'm going to, through kind of algebra and calculus, similar to last time, you can arrive at a similar looking integral that ds by d alpha equals 0, and this ends up being equal to a big integral, where this integral has two big terms. One term looks like the partial of the Lagrangian with respect to x minus d by dt of the partial of Lagrangian with respect to x dot, and that's all being multiplied by epsilon. Then there's another big term that looks like the partial of the Lagrangian with respect to y minus d by dt of the partial with respect to y dot, all multiplied by eta. And that whole big thing is being integrated over your path. So remember essentially last time we had an integral that just looked like this part here. It was the integral of the highlighted part. And we made an argument that if this entire thing is equal to 0, that can, for an arbitrary eta, that can only be true if it is always the case that this thing that's being highlighted is 0. And then we call that the Euler-Lagrange equation. Now we've got a similar thing where we got this entire big thing that when we integrate it is equal to 0. But we have essentially two terms. One term that kind of looks like a Lagrangian with respect to x multiplied by an arbitrary epsilon, and then another Lagrangian with respect to y multiplied by an arbitrary eta. And this entire integral has to equal 0, again, no matter what eta is and no matter what epsilon is. So whatever you can dream up for epsilon and eta, and they don't have to be the same, they can be different, they can be whatever you want. This integral always has to add up to 0. And so similarly, we can say that this can only be true if each of these things in parentheses are identically 0. Where before we had just this, and we said it has to be the case that this is equal to 0. Now we are saying that this and this have to be identically equal to 0. And if there were 3 variables, we'd have another thing that looks like the Lagrangian, dl by dz minus d by dt of dl by dz dot. That would have to be equal to 0. No matter how many variables we have, we'll have a Lagrangian for each of those coordinates, and we can conclude that this is true only if each Euler-Lagrange equation is identically 0. So in this case, dl by dx must equal d by dt of dl by dx dot, and dl by dy must equal d by dt of dl by dy dot. Essentially, for every coordinate you have, there is a Euler-Lagrange equation that is satisfied for that coordinate. And so then we're going to write down in general for n coordinates, they're the q sub i's, or whatever your generalized coordinates are, q sub I, dl by dq sub I better equal d by dt of dl by the q sub I dot for each q sub I. I'll just bracket that entire thing, I think. Right, so essentially when you have multiple dimensions, you just have multiple Euler-Lagrange equations, and then you can solve them together in order to solve for the trajectory of your system. Which is kind of nice that the same idea kind of extrapolates to higher dimensions. So going back to our thrown ball example, where we had L as 1/2 m x dot squared plus y dot squared minus mgy. I have x's and I have y's, so I'm going to do two sets of Euler-Lagrange equations. So I have dl by dx actually equals 0. Then I have dl by dx dot. That equals, it looks like m times x dot. Then I take the time derivative of that second one, and that becomes mx double dot. So it looks like this Euler-Lagrange equation says that mx double dot equals 0, which is what we would expect. There's no forces in the horizontal direction, so F equals ma says that mx double dot equals 0. Then we also have dl by dy. That equals negative mg. Then we have dl by dy dot equals my dot. The time derivative of this becomes my double dot. And then it looks like you also have my double dot equals negative g, or negative mg. And again, that's exactly what we would have expected for a ball thrown to the air without air resistance, that the acceleration is just equal to negative g, and you just get the good old kinematics equations from these two. So multiple coordinates, multiple Lagrangians. At this point, you might be noticing that every time we did the dl by dx dot and then took the time derivative, we got something that looked like, ma, in terms of the F equals ma. Similar here, we got my dot, and then the time derivative gave ma in the y direction. And then that ends up being set equal to dl by dy, which this just looks like a force. Then we had something that looks like ma equals a force. So it seems like when we're doing the Euler-Lagrange equation, something seems to be popping out that looks a lot like Newton's laws of motion. In Cartesian coordinates, it's actually easy to show that they are absolutely equivalent. So let's write down, in general, if I have some Euler-Lagrange equation, L, which is t minus u, and it is some function of x, y, z, x dot, y dot, z dot. In Cartesian coordinates, I know that t is some function of x dot, y dot, z dot, 1/2 x dot squared plus y dot squared plus z dot squared. Then u, since it's a potential energy, I know that it is some function only of positions. You go back to our potential energy module, right? It can only be a function of position. So I know that it's going to be some function of x or y and or z. So if that's the case, look at what happens when I evaluate the Euler-Lagrange equation. When I do the partial with respect to, let me just stick with x. And obviously all this is going to be the same for y and z. Well, if I take the partial of t minus u with respect to x, Nothing's going to happen to the kinetic energy because there are no x's in the kinetic energy. So this looks like it just becomes negative the partial with respect to u, the partial of u with respect to x. If I do it with respect to y, it becomes the negative partial of u with respect to y. If I do it for z, it becomes negative the partial of u with respect to z. Well, think about how we connected potential energies to forces. Remember, just off to the side, remember we said that negative the gradient of u equaled the force vector. Where, for example, negative the partial of u with respect to x equals the force in the x direction, for example. So this is nothing other than the force in the x direction. The partial of the Lagrangian with respect to x is just the force in the x direction. The Lagrangian has that kind of encapsulated more or less in the same way the potential energy has the force as a vector encapsulated in it, as long as you take the right partials and maybe there's some negative signs. Now what about the partial with respect to x dot? Well, again, there's no x dots in the potential energy, so this just becomes the partial of t with respect to x dot. But if I know what the kinetic energy should be, 1/2 m x dot squared plus y dot squared plus z dot squared, well, this is just going to be mx dot. Mass times the horizontal velocity, if x is horizontal. Well, that is just momentum. By definition, that's what we call the horizontal momentum in this case. And then the Lagrangian says that I take the time derivative of the partial of Lagrangian with respect to x dot. So that looks like it's just the time derivative of the horizontal momentum at the end of the day. And then Euler-Lagrange ultimately says then, at the end of the day, I get that the time derivative of the horizontal momentum better than equal the force in the horizontal direction. Well, that's just Newton's second law, right? So we are showing that there is an equivalence between evaluating the Euler-Lagrange equation, which remember was based entirely off this idea of action principles. It actually is equivalent to evaluating F equals ma, which was Isaac Newton's formula involving forces. They are actually the same thing. And you can actually do the proof the other way too, right? I kind of started with Lagrange and end up with Newton's second law. You can then start with Newton's second law and show that you can end up back with the idea of the Lagrangian as well. So there is an equivalence between what we are doing here, even though we came about it in very different ways. F equals ma, right, is a very different way of approaching the problem compared to saying nature is taking an optimal path. Yet, we're seeing evidence that maybe there is something here, because this idea of taking an optimal path allowed us to get back to F equals ma. So maybe they are indeed saying something about the same thing. However, again, with the idea of the action principle, it's that you're considering something in a very arbitrary sense, right? You're not specifying, okay, I'm going to think about this in terms of forces or torques or energies or angular momentums, right? These are all things that we kind of mathematically created in order to understand systems, and found that usually there were relationships between them that we had to discover. Forces were related to accelerations, torques were related to angular accelerations, and then there were these things called momentums that were sometimes conserved. And energy is this other thing that we have to come back to as well. The Lagrangian can actually be used to say something even more general about what's going on, where I don't even need to define momentums, angular momentums, torques, all that fun stuff, but they can actually all just very naturally pop out as examples of things that might be conserved or not, for example, in problems. Let's look at the example of a pendulum. Pendulum that has length L, and it's a bob of mass m that swings through some angle. We've talked about this before. This is a one-dimensional problem, so I can write this down in terms of one coordinate. L in this case might be 1/2 ml squared theta dot squared. That ends up being plus if I put my origin at the top. Then all the y's are negative, which is why it's not minus mgl cosine, but then plus mgl cosine of theta. That uniquely specifies my system. As this pendulum swings back and forth, I chose to do it in terms of the coordinate theta. I could have done it in terms of x and y, of course, but I chose to do it in terms of theta, which itself doesn't have units of position, so it's not a position coordinate, but it is defining, in a sense, the position of my configuration. We can define some terms, and that if we think of above, I said that before when I took the derivative of L with respect to x, let me just scroll up, right, we showed that when I did this partial derivative, I got a force. And admittedly, had I not used a Cartesian coordinate that didn't have units of meters, I wouldn't have gotten something that had units of force. But in that case, I did get something that has units of force. So I can ask myself, what is going to be the partial of L with respect to theta? This, in a case, is a position coordinate. In that it doesn't have units of meters, but it is specifying kind of the location of my system. So you can think of this as kind of a general position coordinate, right? Something that doesn't have a dot over it. Where the dots, theta dot is a general kind of velocity coordinate. So rather than position coordinate, I might call this a generalized position coordinate. And so we call this entire thing, we can call this entire thing a generalized force. And that it will not always have units of force, but we can think of, if I take the partial of the Lagrange with respect to a generalized position coordinate, that's a generalized force. Just how, if we scroll up, when I took the partial with respect to x dot, I got a momentum. Then we can think that the partial of the Lagrange with respect to a generalized velocity is going to give me a generalized momentum. So then the partial of L with respect to, say, theta dot, where theta dot is a generalized velocity, then this entire thing we're going to call a generalized momentum. Even though, again, it might not have units of what we think of momentum when we think of like m times v. But the action principle approach actually generalizes this in a nice way. So let's look at this in terms of a pendulum. Right? When I do L with respect to theta, it looks like I just get negative mgl sine of theta. And the partial with respect to theta, so there's no theta dots or anything, right? It's not a time derivative. This I'm calling a generalized force. But notice it has units of torque in this case. All right, this is what we actually would have written down for the torque on the pendulum, right? If we did this using a force analysis, this is the torque. And then when I do with respect to theta dot, I get, looks like I get ml squared theta dot. And that kind of looks like an angular momentum in this case. So it has units of angular momentum, not regular momentum. And then when I take the time derivative of that, I get ml squared theta double dot, which again looks like a lot like a rotational inertia, mr squared, or in this case ml squared times alpha, such that ml squared theta double dot equals negative mgl sine theta, which is indeed what we would have written down if we did I alpha equals torque. But we didn't have to think about polar coordinates or go into this other thing and define this thing called torque that depends on an origin. In this case, for the configuration that we had and for the origin we chose, it all just kind of pops out. All right. So it's not that there are actually torques and forces and all that. You might think like these are completely different things. Actually, they're just kind of different approaches to solving problems. They're all kind of encapsulated as these kind of generalized ideas of how nature is doing some sort of optimization of an action. Let me also show how the action principle also encapsulates within it the idea of conservation laws. That actually, and we'll explore this more in other modules, can say something even more general about conservation laws than what we had before. So let's go back to the ball where the Lagrangian was 1/2 m x dot squared plus y dot squared minus mgy. We said before that the Lagrangian with respect to x dot, right, in this case it ends up being just px, which was mx dot. But then also notice that the partial with Lagrangian with respect to x equals 0, which if we relate that to a generalized force, it's saying that there's no force acting in the x direction. Remember then that when we said there's no external forces acting in the x direction, we expect the horizontal momentum to be conserved. Does this say that? Well, of course it does, because the Lagrangian says that d by dt of dl by x dot better equal the partial of L with respect to x. But this is just d by dt of the horizontal momentum, and then this partial on the right-hand side we just said was 0. So all this says is that the horizontal momentum is a constant. Within this is also still saying there's also ideas of the conservation laws. And this conservation law popped out particularly because we chose a coordinate such that that general position did not appear in the Lagrangian. Notice in this case, there is no x in this Lagrangian, so this partial will always be 0 for that particular coordinate. And then that allowed us to say that whatever this is, the generalized momentum, which in this case just was regular momentum, is conserved. We would not get that in the y direction. In the y direction, the partial with respect to y is not 0, but it's negative mg. And then that relates to the time derivative of the y momentum. Y momentum is changing in this case. It is not conserved in the y direction, but it is conserved in the x direction. Again, all just popping out from the Euler-Lagrange equations. And if you chose different coordinates, you might actually be able to reveal different quantities that are conserved, because if you can choose a coordinate, actually we can write this down more generally. So we can say something about conservation laws. If L, the Lagrangian, is not a function of q sub I, right? So in the example above, x did not appear in the Lagrangian, so the Lagrangian is not a function of x. If L is not a function of q sub I, then the partial of the Lagrangian with respect to q sub I is 0. Therefore, the time derivative of the partial of the Lagrangian with respect to qi dot is equal to 0. That implies the generalized momentum which is the partial with respect to q sub I dot, is conserved. If you can choose your generalized coordinates such that one of the coordinates, the generalized position coordinate, does not appear in the Lagrangian, you can actually say something about conservation underneath that coordinate. Whatever the generalized momentum is for that coordinate, it's conserved. This is getting to a bigger idea that is called Noethier's theorem, based on mathematician Emma Noether. Noether, I think is how you pronounce it, where she worked these ideas of when there is symmetry in equations, like when particular variables do not appear specifically, you can invoke that conservation might actually be the origin of conservation at all, is based on symmetry in equations, which is saying something about how variables may or may not appear in the equations. We'll probably come back to that in a little bit because that's a big theorem in physics. But notice all these beautiful things are popping out from evaluating the Euler-Lagrange. Again, this action principle of nature doing an optimization. We're getting all these things. Where did F equals ma come from? Well, it was just evaluating Euler-Lagrange under Cartesian coordinates, more or less. Torque, relates to inertias and rotational accelerations or angular accelerations. Really is just, again, evaluating Euler-Lagrange, but using a different generalized coordinate. Conservation laws. Where do conservation laws come from? Well, if I can write down the Euler-Lagrange equation in terms of a coordinate such that the generalized position does not appear, I can say something about conserved quantities. So lots and lots of interesting things are popping out, almost naturally. This also allows you, really, as long as you're comfortable with partial derivatives, it really allows you to start solving what would be absurdly challenging problems to do with Newton's second law in a much more efficient and clean way. So let me do two examples, one involving multidimensional motion and then one involving non-inertial reference frames. So let's go and consider this problem. So I have a box on a frictionless surface. It's attached to a rope, which is over a pulley. And then there's another box that's hanging, but it's not necessarily hanging entirely vertical, right? It might be swinging around, at some angle. And let's say they're both mass m to make my life easy. Well, in this case, the number of objects is 2. The number of dimensions is 2, right? Because I have both horizontal and vertical motion going on. But then the number of constraints is also 2. One constraint being that the left box is only horizontal motion, essentially the fact that the table is in the way. And then the second constraint is that the rope is a fixed length. So there is a relationship then between the positions of the two boxes. So then the dimensionality I expect to be 2 times 2 minus 2, or 2. I should be able to write everything in terms of 2 coordinates. And what those coordinates are, I now have to think about what would make the most sense. Well, since the hanging box is swinging and it has some distance r from the pulley, I might put my origin for that box at the pulley, and then polar coordinates might make the most sense for writing down what's going on with that hanging box. But then for the horizontal box, right, I might have my origin for the horizontal box here, and then I can specify its location by some x value. And then similarly, the pulley is some distance x sub p, which is a constant, relative to that origin. under these definitions, the length of the rope then looks like it's going to be x sub p minus x plus whatever r is. And that gives me the full length of the rope in this case, where L rope is a constant, so is x sub p. And if this were a Newton law problem, we would say that this gives me an acceleration relationship between x and r, namely that x double dot equals r double dot. But now let's think if we wanted to write this down in terms of Lagrangian. Maybe my goal is to use x and theta as my general coordinates, as my q sub I. Or you could use r and theta as well if you wanted to. You could do x and r, I guess, as well, but there would be some messy arctangents or something like that if you wanted to get rid of the thetas. But you could do that as well. Well, to write down the Lagrangian, I have to first write down my kinetic energy. And so the kinetic energy of the horizontal box is going to be 1/2 mx dot squared, because I can only move horizontally. And then the kinetic energy for the hanging box is going to be 1/2. Then if I'm using polar coordinates, the polar v squared is r dot squared plus r theta dot all squared. And that gives me my total kinetic energy. My total potential energy, there's no springs involved, so there's only really gravity. Since the horizontal box is not changing its height at all, I know there's going to be no change in potential energy there. So if the origin is at the pulley, it looks like this is mgr cosine theta. Negative mgy, but y in this case looks like it's going to be r cosine theta with how far down below the pulley the box is. Then the Lagrangian looks like it's 1/2 m x dot squared plus r dot squared plus r squared theta dot squared plus mgr cosine of theta. Now, of course, the Lagrangian in this case is still written in terms of 3 coordinates, x, r, and theta. If I claim the dimensionality is 2, I should be able to write this entire thing in terms of just x and theta. Well, that's where our constraint comes in, because then I can write this as 1/2 m x dot squared. And then the rope relationship says that r is going to be equal to x minus x sub p plus L. So then r dot is going to be x dot, since x sub p and L are constants. So in this case, this looks like this is also just equal to x dot squared. And then plus, then I have r is x minus x sub p plus L all squared multiplied by theta dot squared. Then I've added to that mg x minus x sub p plus L all times cosine of theta. This then gives me the full Lagrangian I've written in terms of only x, theta, x dot, and theta dot in this case. And t does not appear explicitly at all. All right. That took some work, but now I have this one function that's written in terms of my 2 coordinates. Now, all I do is just crunch through the machinery of Lagrange's equation. So let me do theta first. So dl by d theta. If I scan through, looks like theta only appears as that cosine theta. So this looks like it's going to be negative mg x minus xp plus L sine of theta. Then dl by d theta dot. Looks like there's only one theta dot that appears, so it looks like there's going to be an m x minus xp plus L all squared theta dot. But now I have to be careful, because when I take the time derivative of this, notice that in this case, x is still hanging around. So I can't just write that as mx minus xp plus L squared theta double dot, because x is also a function of time. So then I have to do, it looks like this could be 2mx minus x sub, what do I call this? P plus L theta dot. And then the chain rule that's multiplied by 1 plus m x minus xp plus L squared theta double dot in this case. So not too bad, but it does look a little bit more complicated. So in this case, let's see, have we completed everything correctly? Yes, I believe so. So then the first Euler-Lagrange equation says that it looks like 2m x minus xp plus L theta dot plus m x minus xp plus L squared theta double dot equals negative mg x minus xp plus L sine theta. That is one of the two Euler-Lagrange equations that you have to solve. Notice it's coupled, right? It's not just a function of theta, but it has x in it as well. So I need to simultaneously come up with a differential equation for x, and then I would solve those together, most likely on a computer. We could also ask ourselves, like, does this equation make sense in the limit that, if this is just a pendulum, then some of these variables become constants, and I'll let you work that out and see, like, does this actually come back to just becoming a simple pendulum in that limit as well. Then the second set is I have to then do everything with respect to x. So my Lagrangian up top, let's see. Oh, it does have an x in it. So I can't just say that this is equal to 0. It looks like this is going to be m x minus xp plus L theta dot squared. That's the first term. Then it also looks like it's going to be mg cosine of theta as well. When I properly take the derivative with respect to x. Then when I take the derivative with respect to x dot, it looks like that just becomes 2mx dot. Then when I take the time derivative of this, that actually just becomes 2mx double dot, which is not too bad. So my second Euler-Lagrange equation looks like it's 2mx double dot equals mg cosine theta plus m x minus xp plus L not all squared, but multiplied by theta dot squared. Oof. So with the aid of a computer, this actually then wouldn't be too hard to solve, and you could solve for the motion of the two boxes, right? You could get x as a function of time and theta as a function of time, and then using the constraint equation, get r as a function of time. And then that would then be the solution to your system. But again, deriving these two equations using Newton's laws of motion would have been quite the headache. And you might think that this was still a headache, but I assure you this is much, much more straightforward than, say, what you would have had to do, using Newton's laws. Let me do one more. So again, just like before, you need to evaluate the Lagrangian in an inertial frame. However, some of your coordinates that you use could be non-inertial coordinates. So let's take the example of, we have a car that has a box attached to a spring, where the spring is attached to the front of the car. The box has a mass m. The spring has a spring constant k. And let's say that the front is where the force of the spring equals 0, where it's neither stretched nor compressed. But this entire car is accelerating forward with some constant acceleration a. And I would like to know, from the point of view of someone in the car, what would they say is happening with the box? And if you watch the non-inertial frame module, right, to someone that's kind of hanging out on the car looking at what the box is doing, right, they would say they're not in an inertial frame. So if you measured x, say from the front of the car, so this blue arrow here corresponds to x, your position. So I'm putting my origin kind of at the front. They would have said that m little x double dot is equal to negative kx, but also they would have to add in a fictitious force, and they would say that it's equal to negative little m times a. Because they are not in an inertial reference frame, because the car is accelerating. What can we still pop this out naturally using Lagrangians? So we can. This is getting kind of busy, so let me redraw. But now let's have someone be an inertial viewer over here, and they are watching the car move forward, and it's accelerating forward. And they want to now get an equation of motion for this little x, like what I drew in blue on the left picture. Well, this is a one-dimensional configuration. It's only moving horizontally. So I expect to be able to write everything down in terms of a single coordinate. But I also need to take into account the fact that the car itself is accelerating forward. So the way you might do that is, if you have your inertial viewer here, they might identify the location of the box, not just by drawing a vector going from them to the box, but they might first identify the location of the box as first going to the front of the car, so that's maybe x sub car, and then from there going backwards to the location of the box. So then box is at x sub car plus x in this case, vectorially. All right, that's all well and good. These aren't two separate coordinates though, because the position of the car, if it's accelerating forward, we can write down a formula for the acceleration, for the position of the car moving forward. All right, since car is accelerating, you might write that x sub car is 1/2 at squared, or something like that. At t equals 0, the car is right at the same position you are, and then it's moving to the right. And since it's accelerating, its position is given by this simple kinematic equation. So in that case, then, the box itself is located at 1/2 at squared plus whatever x is. And x in this case is going to be a negative number, but again, I'm thinking vectors, so I'm still just adding it. So I'm going to plug in negative numbers for x. This then allows me to write the position of the box from an inertial observer, the person standing outside the car, but the way that they are writing down the position of the box incorporates this lowercase x, which was the same coordinate as the blue person that was just sitting on the car viewing what's happening in the box from a non-inertial reference frame. So by using that coordinate, even though it's a non-inertial coordinate, we're viewing everything from an inertial frame. We can still employ Lagrange's equations. So in this case, the kinetic energy is 1/2 m x box dot squared. So that looks like it's going to be 1/2 m a t plus x dot all squared. Or if I multiply that entire thing out, 1/2 m a squared t squared plus 2 a t x dot plus x dot squared. Then the potential energy, since it's just coming from the spring, and the spring is not stretched and compressed at the front of the car, is just going to be 1/2 k little x squared. Again, this coordinate choice then makes my life simpler, and that's easy to write down the potential energy. The Lagrangian then looks like it's 1/2 m a squared t squared plus x dot squared plus the cross term 2a t x dot minus 1/2 k x squared. And that is my Lagrangian. I'm out of room, so let me copy it. Go over to the other page. This is written entirely in terms of my one coordinate. It is viewed from an inertial frame. I'm off and running. The Lagrangian with respect to x looks like it's just negative kx. Lagrangian with respect to x dot looks like it's going to be mx dot. Then there's this cross term plus 1/2 m, then 2at. This is the partial with respect to x dot. So that looks like mx dot plus, I guess, mat. I then take the time derivative of that entire thing, and it becomes mx double dot plus ma, which is a constant, and the t just becomes unity. And look at that. Lagrange then says mx double dot plus m big A equals negative kx, or mx double dot equals negative kx plus what we would have called before a fictitious force, because we're trying to do things in a non-inertial reference frame. Again, it just all pops out by doing Lagrangian dynamics correctly. The challenge, of course, is choosing the right coordinates, right? You can always choose whatever coordinates you want, but there are some that are subjectively better than others. Depends on how you're trying to simplify the problem, e.g. looking for conservation laws, or if you're trying to do, for example, a question involving relative motion, can you write down your Lagrangian where that relative motion coordinate is one of your q sub i's? If you can, then Lagrangian dynamics might be able to say something interesting without having to resort to relative motions or all the stuff we did before. All right. Now, those were only a couple examples. It's time to go practice doing these things.